Let's take a minute to talk a little bit more about pressure. We mentioned in the last lesson that pressure is the force of collision between the gas molecules and the container. But let's talk a little, that's probably a measurement that you're not used to making really often. Matter of fact, how would you go about measuring that? Well, we measure it by means of a couple of devices called manometers and barometers. A manometer will measure the pressure of the gas in a container. Let's say that you have a sidearm flask, and this sidearm flask has a rubber stopper in it, and it contains gas, widely separated particles, and they're moving in random directions. Here a little, there a little, everywhere a little. All right, to this, we're going to hook up our manometer, which is basically a J-shaped tube. And in that tube, we have, down in the bottom, of course, some mercury. Okay? As these particles bounce around, some of them are going to wind up bouncing down into this tube and smacking into the mercury, which is going to push the mercury down on this side and up on this side. So we may wind up with the mercury, say, in this position. Now, the difference in height right there is going to be directly proportional to how hard it was hit by how many particles over here on this surface. And so this will give us our millimeters of mercury, which is our measurement of pressure. Right? If what we want to measure is not the pressure inside a container, but the pressure of the atmosphere, then we'll use a barometer. The first barometers, this is not very safe, so this is not how we do them anymore, consisted of a container of mercury, and in that container, an upside down tube, very long test tube that was filled completely with mercury, stoppered, and then turned upside down into this bowl of mercury. So we wind up with mercury in the bowl, and by the way, mercury has a negative meniscus. It doesn't like glass, and so it actually moves slightly away from glass, and you get this curve that's upside down from a water meniscus. All right, and some of the mercury that was up here in the tube is going to be pulled down by gravity and fill the bowl a little bit more. However, we also have the gas of the atmosphere, which is bouncing around out here and pressing on this surface of the mercury. And there's nowhere else for this mercury to go except back up the test tube. And so at some point we'll reach an equilibrium where gravity is pulling the mercury down out of the test tube, atmospheric pressure is pushing the mercury back up into the test tube, and so the mercury will hold its position. It will stay at that position. And then all we do is just measure the height of this column of mercury, and that is our barometric pressure. That's the atmospheric pressure on that particular day in that particular place. It's related to the weather. If you've ever listened to a weather report or looked at a weather report on your phone, it always tells you the barometric pressure and whether it's rising or falling. That tells you something about, is cold air descending on top of this barometer, or is hot air rising away from the surface of the mercury? Now, we don't actually use this kind of barometer anymore because having that amount of exposed mercury is really dumb. Instead, we use an aneroid barometer. Those are tricky. They involve springs and levers and pulleys and linkages and all kinds of stuff. But you can get a general idea of it if you think of a rigid container, and over this rigid container, we're going to stretch a balloon or some thin rubber sheet. And to the end of the center of this, we're going to glue a bamboo skewer, a chopstick, something of the sort. Okay? And then over here we'll stand a ruler. There's our ruler. Now, if we've got a certain amount of air trapped here inside the container, and then we have air out here in the atmosphere. The amount of air inside the container can't change. It can't get out of the container. More air can't get in because this balloon is in the way. And so if the pressure outside decreases and we have more pressure on the inside, that's going to cause our balloon to slightly bulge upwards, which is going to cause our pointer to point downward a bit, and it will show you a lower value for its pressure. If the atmospheric pressure becomes greater than the pressure here inside our container, that's going to cause our balloon to be caved in to the container a little bit, which means that our pointer is going to point to a higher pressure. Okay, so this is a very simple kind of barometer to make. My Cub Scouts make it every year. Now, as they come along and we talk about weather, we make a little simple barometer. So this is an aneroid barometer, not the kind that a real meteorologist would use, but you know, you get the idea. All right, what are the units that pressure is measured in? Well, we have several times referred to millimeters of mercury, because we're just measuring the height of that mercury column. But of course, this is science. We can't just call it millimeters of mercury. That's too straightforward. We've got to name it in honor of some great scientist in hopes that someday somebody will name a unit after us. Well, this unit has been renamed in honor of Torricelli, who was one of the early researchers in gases and pressure and whatnot. And that being kind of a long word, we call it a torr. Okay, so a millimeter of mercury is the same thing as a torr. The normal atmospheric pressure at sea level when the temperature is 0 degrees is 760 torr. Okay? Now, of course, in the United States, you're going to see this reported as inches of mercury, and we're not going to worry about that. This is chemistry. We're SI. We're not fooling with inches. We're going to stick to millimeters. This can also be measured in atmospheres, where 760 torr would be the same thing as 1 atmosphere, the usual pressure on a freezing beach. Or it may be measured in pascals or kilopascals. The abbreviation here is kind of interesting because kilo is little k. Pascal, though, is the name of a person, and so it should be capitalized. And so a kilopascal has a capital P in the middle and lowercase letters on each side, and it looks a little weird, but that's okay. We can easily convert from one of these to another if we realize that 1 atmosphere is the same thing as 760 torr, which is the same thing as 101.325 kilopascals. This means that we can write unit multipliers. We can say 1 atmosphere over 760 torr, and that's a secret identity of 1. Or we could say 760 torr over 1 atmosphere, another secret identity of 1. Or 760 torr over 101.325 kilopascals. Or the other way around. You can get a whole variety of unit multipliers here. And so it's very easy to convert from one unit to another. For example, if we had a pressure of 740 torr and we wanted to change that to kilopascals, we just set up for a unit multiplier. We put torr on the bottom so that it will cancel with the torr we've already got. We put kilopascals in the numerator so that that's the unit we'll wind up with. We know that 101.325 kilopascals is the same thing as 760 torr. The torrs cancel out and you just let your fingers do the walking on the calculator, and there you have it. All right, one more little nugget of information that I need to give you. We have standard temperature and pressure. sometimes we're not terribly concerned with the exact conditions at the exact time and place that we're located. We just kind of want to talk about the usual situation. Well, that's the standard temperature and pressure, and it's abbreviated STP, which in the chemistry lab is not a gasoline additive. Standard temperature and pressure is defined as 1 atmosphere of pressure and 0 degrees Celsius. In other words, we're on that freezing beach. Well, we don't actually do a lot of chemistry on freezing beaches. It's kind of uncomfortable and the sand gets all in your glassware. But we will still often work problems as if we were. And so anytime you see in a problem that it's at standard temperature and pressure, we mean 1 atmosphere, 760 torr, 101.325 kilopascals, and 0 degrees Celsius, 273 kelvins. And that's just a very quick way for them to specify conditions that all chemists work with all the time. And that will probably do it for today.